Okay, let me introduce Eamon again. Who will speak on F-jumping numbers and monodromy eigenvalues. Here.
Thank you so much. Let me thank the organizers for the opportunity to speak here. I'm of course thrilled to be able to talk in a conference in the honor of Karen.
Speak louder.
Oh, okay. So I just wanted to share that over the last couple of days as I was preparing for this talk, I found myself thinking a lot about, oh, would Karen like if I presented things this way or that way? And it felt like a fun throwback to the time when I was a grad student. More generally, let me say, so since I left Michigan, I've always tried to keep small Karen in my head and keep all her advice as alive as possible. And whenever that small Karen tells me to do examples, do you really understand this deeply? I find that whenever I listen to her, things turn out better for me. So thank you, Karen, for being such a good influence mathematically and in other ways. Okay, so the theorem I want to talk about today, I will eventually state as a theorem in commutative algebra and in the language of F singularities. But the motivation for the theorem, which is very dear to my heart, actually comes from the study of topology of singularities in characteristic zero. So what I want to start with today is just explaining the motivating theorem. And then I want to explain a characteristic P analog of this theorem and eventually explain how this turns into a commutative algebra F singularities problem. Okay, so let me start with some notation for the rest of the talk. So K will be an algebraically closed field of characteristic P. And I will, for the motivation part, I will allow P to be 0. F will be a polynomial in n variables over K, which is homogeneous of degree D in at least 2 variables. Let me assume that P does not divide D, which of course is automatic when P is 0, but meaningful otherwise. And I want to assume that it also has an isolated singularity. Meaning that if I take the ideal generated by the partial derivatives of F, I get an M primary ideal. Okay, so what do I want to do with this F? So this F defines for us a map from AN to A1. By the fact that I do it vertically, you probably guessed that I want to think of it as defining some kind of family. And I want to draw what this family looks like when K is the field of complex numbers. So when K is the field of complex numbers, we should think of this A1 as really a complex plane. So let me draw a plane here in the base. And then I want to think about fibers over points. So first, if I take the fiber above 0, I get by definition the vanishing locus of F. And now by virtue of the fact that F is a homogeneous polynomial, it turns out that if you take any fiber away from 0, you will get isomorphic varieties. Basically because the grading induces a C-star action that you can use to scale one fiber into another. So okay, so away from 0, these varieties look the same, and whenever you have this kind of situation, you get this monodromy phenomenon. So let me briefly say what this means. So suppose I start at some fiber at some point in the complex plane, and I take a loop around 0. What I can then do is I can take, if I take any point on this fiber here, right? By the way, let me call this fiber here YF circ. So if I take any point of YF circ, I can trace around how this point moves as I move around the loop downstairs. And the point is that you might not come back to the point you started with. So this defines an automorphism T that I want to call T of this YF circ, and this automorphism is called monodromy. Okay, so back to general notation, I said that this YF circ is the fiber above any non-zero point, and you can take your favorite complex number, but in my case, that's 1. So this is the variety defined by F equals 1, living on a half space. Now, this is not so important in characteristic 0, but it will be in characteristic P. So what I want to do is actually compactify this fiber. And the way you do that is you consider the equation F equals y to the d, where remember d is the degree of F, and you think of this, you think now of this as living in very good space over here. So let me just point out that this is now a smooth projected hypersurface. of dimension n minus 1. And with this notation describing this monodromy automorphism is actually pretty straightforward. So let me fix a primitive d root of unity. Then this automorphism T can be just defined pretty explicitly on homogeneous coordinates. I have homogeneous coordinates x1 through xn and y. What you want to do is you want to leave the x's fixed and you want to multiply y by theta inverse. Okay, so maybe it's more natural to, if you do this computation, you'll want to put a theta on all the x's and leave the y intact. But of course, we're in projective space, so that's really the same as doing this. And this description will be sort of better for later services. Okay, so with this, let me tell you the theorem that I want to talk about. So as I said, this is a theorem in characteristic 0, and I'm also going to be implicitly assuming that we're picking this sort of standard primitive d through d. Okay, so what's the point of this theorem? The point is we would like to understand the action of this endomorphism T on this variety YF, or more precisely on its cohomology. And the point is that there's an invariant that actually captures this information, and it's already appeared in a previous talk, and it's called the Bernstein-Sato polynomial. So let me denote BFS. The Bernstein-Sato polynomial is F. And what this is really just you can say a lot about this polynomial. Let me just say for our purposes, just think of it as a polynomial with complex coefficients. And maybe in case you've seen this just once and I want to recall, so this polynomial satisfies a functional equation of this form, where this P of S is a differential operator, right? And you take the smallest monic polynomial that satisfies such a functional equation. This is called the Bernstein-Sato polynomial. So maybe what I want to say about this polynomial is that, especially in the case of homogeneous polynomials with an isolated singularity, but even more generally, there's algorithms to compute this Bernstein-Sato polynomial that are implemented, for example, in my colleagues. Okay, so with that, here's the theorem that motivates our work, and it was proved independently by Kashiwara and Malgrange in 1986. And it says that if you take the collection e to the 2 pi I alpha, where alpha ranges through all the roots of this Bernstein-Sato polynomial, you get the eigenvalues of this action of monodromy under cohomology. And by cohomology, I mean the singular cohomology y with complex coefficients. Okay, maybe just a quick comment. So here I put n-1. The theorem stays true if you take the direct sum of all the cohomology groups. The point is that there's this theorem of Lefschetz that tells you that for a smooth hypersurface, really the only interesting cohomology is this so-called middle cohomology. And so this is the only cohomology group that can really have any non-trivial eigenvalues. Okay. So with this, let me describe now what we can prove in characteristic P. All right, so I mentioned I want to prove an analog of this result. And if you want to prove a characteristic P analog, you want a characteristic P analog of the left-hand side, you want a characteristic P analog of the right-hand side, and you want to hope that they're equal to each other. The analog of the left-hand side is very dear to my heart, but I don't have enough time to really talk about it in detail. Let me just say the following. So, Bitun in 2018, influenced heavily by previous work of Mircea Mustata, constructed an analog of this B function in positive characteristic. And the theory is a little bit quirky. One of the quirks of the theory is that one only can define an analog of the roots of the B function, but not necessarily the B function itself. So these I want to call today the Bernstein subtle roots of them. So there are some characteristic p-analog of the roots of the Bernstein subtle polynomial. But then, so what we do prove is actually, so these, even though they're defined in a completely different way, they turn out to be invariants that are familiar to people in F singularities. So what this turns out to be is you take the F jumping numbers of F, which also appeared in Kevin's talk. Thank you, Kevin. So these are the jumping numbers of the test ideal that Kevin introduced in this talk. And what you want to do is you want to take the ones that have whose denominator is not divisible by p, and that lie inside the interval 0, 1. And you take those and you put a minus sign in front of those, and this gives you this characteristic p-analog of the roots of the b function. Now, one thing I'll say is that, yes, I don't have time to go into this. Maybe for the purpose of this talk, it's good enough to take this as definition and just believe that they provided somehow satisfactory analog for this. Okay. So we have an analog of the left-hand side. For the right-hand side, we want an analog of singular cohomology for varieties in characteristic T. And as you might be aware, that's a very long story starting with the wave conjectures. And there's many sort of cohomology theories that one could use. All I want to say here is that for smooth projective varieties like this Y, there is one that works pretty well, and that's called crystalline cohomology. So on this side, we're gonna consider the crystalline cohomology of Y. So to state the theorem, let me just a couple more pieces of notation. So W will be the ring of bit vectors of K, and capital K will be the fraction field of this W. And just because I don't have access to this sort of standard T-root of unity, the theorem will be a little bit more clunky to state, but it's really saying that something very similar to this. So let me say, fix a permitted root of unity in K. Okay. Maybe one thing about this choice. So the theorem really doesn't depend on this choice. There's a way of stating the theorem that doesn't make reference to such a choice. But I wanted to avoid some language from representation theory, just so that just keep it more than anything. So yeah. Let me state this theorem. We'll call it theorem 1. And it says the following. So first of all, the Bernsteins have the roots of F, or in other words, these F jumping numbers that have no p in the denominator really live. But the point is that they can only have d in the denominator. So this lies in the set -1 minus d plus 1 over d, all the way until. So let me say, at least for the F-pure threshold, this was already known by work of Daniel Hernandez, Luis Núñez de Betancourt, Emily Weed, and Wenliang Jan.
Wound up skipping some slides because I ran out of time, but on the whole, doing very well.
Sounds
And it was kind of fun.
Okay, we'll take that as a comment from Mel. Great. So as I was saying, for the F-pure threshold, this was already known that when the F-pure threshold has no p in the denominator, then the denominator is d. As far as I know, this might be new for other F-jumping numbers, but if it's not new, certainly someone in the room knows that this is not true, so please let me know. But anyway, with this result, we can now state it forward. So I take out to the alpha d, where alpha ranges through all these Bernsteins at the roots. We get the eigenvalues for the action of monodromy on now the crystalline cohomology of Y, answered up to K. But now, crucially, we don't get the action of T on the whole crystalline cohomology group, but rather on the slope 0 part. And I'll say more about that in a minute. Okay.
Wait, can I make sure I understand one? Are you saying if, well, I mean, you're probably saying more than this, but you're saying if I have a homogeneous polynomial of degree d
with isolated
singularity, and I'm in characteristic P doesn't divide the characteristic of D,
Yeah.
then all of the F jumping numbers in that first range, 0 and 1, have denominator D, they're one of these?
Oh, no, the ones that, okay, maybe another way to state it is if an F jumping number has no D in the denominator, then it must have a P in the denominator. Is that okay? So,
I didn't know that. That sounds
yeah, so
surprisingly.
yeah, so let me say there's counterexamples to that. So maybe, yeah, there's counterexamples to that, but none of them that are even quasi-homogeneous. You can have, for example, the F threshold not have a P in the denominator and not be equal to the log canonical threshold, but that never happens for these kind of polynomials. Okay. Okay, so what I want to do next is take this theorem that involves some kind of complicated machinery and turn it into a theorem of F singularities in commutative algebra. For that, let me just introduce some notations. So if we're going to do commutative algebra, we need a commutative ring. And the ring in question is going to be the coordinate ring of this variety Y, or I guess, starting to graph the subscripts. Okay, so just to be explicit, so this is a polynomial ring in variables x1 through xn. Y added, and then I kill the equation y to the d minus. Okay. With that, I can state, let me call it theorem 2. It's really, as I said, the same theorem, but just stated in commutative algebra language. Okay, so maybe just to emphasize the point that I want to move away from this B function and crystalline cohomology language, let me replace these B functions by using Beaton's theorem really by F jumping numbers. So what it says really is that the F jumping numbers of F that have no P in the denominator and that lie in the interval between 0 and 1 agree with the fractions A over D, where A ranges between 1 and D, and when I consider the top local cohomology of the string R, that's supported in this homogeneous maximal ideal, and I take the degree 0 piece, and I take the eigenspace on which T acts by theta to the minus A, then this subspace of top local cohomology is not Frobenius inequality. So this is the commutative algebra version. Okay, so what I would like to do next is to explain why theorem 1 and theorem 2 are equivalent. Here the equivalent. Theorem 1 and theorem 2. Okay, so let me start by fixing an integer e, such that d divides e to the e minus 1. Okay, if we want to relate theorem 1 and theorem 2, right, we want to relate these Bernstein's upper roots with the F jumping numbers. That's already done for us by Beaton. The next step is to relate the eigenspaces of this crystalline cohomology group and the eigenspaces of this top local cohomology Y.
And we can ask a stupid question.
Oh.
So for the eigenspace decomposition is respected by Frobenius? Is that?
Oh.
So you say it's not Frobenius influence, Frobenius act on that?
So Frobenius, so okay. One way to state this is Frobenius acts certainly on local cohomology, and I'm saying that if I take anything inside of that subspace and I apply Frobenius long enough, or high enough power of Frobenius, even if I go outside this subspace, I get zero. That's one way to state it. If you want to actually Frobenius to act on this, you need to do F to the E, where E is that integer there. And then F to the E will respect the eigenspaces. That okay?
That clarifies it.
Thank you. All right. So let me now hint at why this crystalline cohomology group is related to this top local cohomology. Okay. So let me start with lovely question. This is the crystalline cohomology group and the slope 0 is. Okay. So I haven't really defined this crystalline cohomology. Let me give you a sense of what kind of object this is at least. So this piece here is a finitely generated W module equipped with a Frobenius action. And when you extend such a module up to K, it's just a general theorem that your module will split into something that looks like a generalized eigenspace decomposition for the action of Frobenius. So I'm not gonna. So this is, you should think of this really as a generalized eigenspace for the action of Frobenius. But maybe to be even more concrete, let me tell you what this actually is. So at least the slope 0 part is not too bad to define. So you take this y over w. Let me give myself some more space. Right, so you want to take the homology classes that are fixed by Frobenius, and then you want to take the k-span of them, in that case. So if I want to understand whether an eigenspace for the action of t is 0 on this, all I need to understand is whether that eigenspace is 0 here. Right, but now, to understand whether a module is 0 or not 0, I can go on p. And one of the key facts about this crystalline cohomology is that if you reduce with mod p, okay. Sorry, so here I want to make some simplifying assumption. I want to assume that the crystalline cohomology groups of Y are p torsion free. We don't need it, but it just makes the discussion a little bit easier. So under that assumption, if you kill p in one of these crystalline cohomology groups, you get the Durand cohomology of Y with coefficients in them. Right, and what this really is the hypercohomology of the Durand complex on Y. Okay, so now this requires a bit of an argument, but please believe me that the same is true if you take Frobenius fixed parts on both sides. Okay, so next, let's think about the Durand complex and how Frobenius acts on it. Right, so the Durand complex, it starts with OY, and then it has all these higher differential forms. But the point is that Frobenius acts by 0 on higher differential forms. So the only thing that can really contribute to this Durand cohomology group is the OY piece. So this is actually the same as coherent cohomology of Y with coefficients in OY, and again Frobenius. So what I said here, it was really just intuition. If you want to make it precise, you have to do a spectral sequence argument. Okay, and now we're almost there, right? So if you've never seen this fact, I like it a lot. So whenever you're trying to compute coherent cohomology of something, you can actually instead compute topolocal cohomology as the coordinate. So this is really, even without Frobenius fixed coordinates, this is the topolocal cohomology of R in degree 0. But now, because I am taking Frobenius fixed points, really any Frobenius fixed thing has to have degree 0, and so there's our connection. Now, to finish, let me mention, so everything in this picture is T equivariant. So now if I restrict to an eigenspace for the action of T, everything goes through. And there's your connection, right? So this is 0, if and only if this is 0. The only minor detail that's left is that here I didn't write Frobenius fixed points is non-zero. I wrote that the corresponding piece is not Frobenius nilpotent, but this is just a sort of fact in P linear algebra that when you have a finite dimensional vector space equipped with a Frobenius action, the existence of Frobenius fixed point is equivalent to the non-nilpotency of Frobenius. Okay, so that's why theorem 1 and theorem 2 are actually the same theorem.
Sorry, is Y the special form or what's Y?
Oh, sorry, y is y sub f,
Y sub F, okay, yeah.
which was this
the second
equation.
guess, yeah. Oh. So it's speckle.
It's Frobenius.
Frobenius.
YF is Frobenius.
Okay.
Okay, so I have a few minutes left. I want to talk about, right, I told you why theorem 1 and theorem 2 are the same, but you still have to prove theorem 2. So let me tell you then what are the key ideas for theorem 2. Okay. So one of them is, right, we want to understand total cohomology of this ring R. And it's just really how to find a k-basis for this. So what you do is you notice that if you just consider the polynomial ring in the x's, this provides a node for normalization for this ring. And so another way to say this is that if I want to compute topolocal cohomology, I can consider the check complex on the x's because the y is sort of primary to that. So that's what I'm going to do. So now it suffices to compute the topolocal cohomology of R when viewed as a module for this polynomial ring. But now this ring is free for over this one in the powers of y. So if you've ever computed the topolocal cohomology of a polynomial ring, all you need to do is add the powers of y. So let me just see what you get here. So you get the k-span of classes. I'm using again the check complex on the x's, y to the a over x1, x1, xn1 plus bn, where the a ranges between 0 and b minus 1, and the bi's are all positive. Okay, but now these, then we get lucky, right? Because this action that I did here is sort of rigged so that these are actually eigenvectors for the action of this thing. So here, on such a cohomology class, T acts by theta to the minus a. It fixes the x's and then it multiplies y by theta. And then you can actually just compute, right? So you give yourself these cohomology classes in degree 0, and you ask yourself, under what conditions can I kill these by Frobenius? Let me say just a couple more things. So first, there's a key lemma that then goes into the proof that might be of independent interest. So we prove that when you take a rational number with no p in the denominator, the test ideal of f to the lambda minus epsilon, right? So this one. So if I take high enough degrees on the test ideal of f to the lambda minus epsilon, I recover the test ideal for f to the lambda, and that's independent of whether lambda is an f-jumping number or not. So when lambda is an f-jumping number, what this is telling me is that the difference between these two test ideals has to land in this, has to be of small degrees. And let me say, of course, this is all still under this homogeneous isolated singularity assumption. Okay, and just to finish, let me address why is it still in progress, or in some sense, how could you choose to push this or hope to push this? The point is that this theorem in characteristics here is actually a bit more general. So even without the assumption that f is homogeneous and has an isolated singularity, it's true if you replace this homology group by what is called the sheaf of nearby cycles. And so one could hope that you can push this theorem by making an appropriate replacement here, but we don't know sort of what this replacement could be. And finally, let me say also that this theory of B function in characteristic P is still a little unsatisfying, because by this theorem of P2, all the roots but lie between -1 and 0. And in characteristic 0, roots that are smaller than -1 actually can carry a lot of information about the singularities of F. So one could hope that there's a better definition of Bernstein set of roots that actually captures more of these invariants. And this theorem actually points you in that direction too, right? It says that you're only capturing really the slope 0 part of this crystalline homology. One could hope that a better definition of this would capture all the eigenvalues, even in the higher slopes. Okay, and that's all. Thank you very much.
Thank you, Eamon. Are there any questions for Eamon? That's one already.
Yeah, so you mentioned that you need to kind of projectivize for the characteristic P situation. Is the only obstacle to that the fact that crystalline cohomology isn't well behaved for something that's not projected?
That's right.
Proper?
Yeah, that's right. So I think, for example, if you use rigid cohomology instead of crystalline cohomology, I think you would not need to projectivize. Basically, you have this excision exact sequence that
More questions? Kevin?
Any hope of doing quasi-homogeneous instead of homogeneous?
Yes, so this has been the vein of my existence for a while. So there's reasonable hope, at least coming from characteristic zero, that the quasi-homogeneous case could also be easy. The problem is that this YF that I constructed is not smooth for quasi-homogeneous things. So I don't know how to produce a good
Right.
compact.
It's toroidal, so it shouldn't.
Shouldn't, maybe it's okay? Yeah.
That's the situation.
Two is okay.
It shouldn't be.
Oh, yes, so two,
I don't know about theorem one.
that's right, okay, sorry, so I think, I'm trying to recall. Theorem two, we do have a version for quasi-homogeneous with singularity, but the relationship between this crystalline cohomology and local cohomology comes through this fact that mod P of crystalline is norm. And I don't know if that's true when your variety has singularities. That's the instruction.
More questions? Karen?
I didn't catch your collaborators' names.
Oh, so that, okay.
Well, you might have said them. but just-
So Hiroki Kato is one. That's a good place. And Daichi Takeuchi is the other.
Okay. Well, let's thank you again.
Thank you.